action, and then actually it could be like a very dramatic change along the way because each node is independent of each other. So yeah, interesting. It will affect the result. Like, okay, thanks.
Yeah, yeah. Yeah, by the way, I realized that I forgot to turn on the recording, so now we are recording. Okay. All right, so any other questions? Yes, Ahmed.
Hey, John, thanks for the presentation. So actually my question regarding the future release of the solid transport module, um, when it's released, is there any benchmark problem will be available with those, with the release, or like to compare that modules with any other code for verification?
Well, Udita is online. I don't know, Udita, if you heard the question, maybe he can answer that because he's the one developing everything about it.
Yeah, I think I heard the question. I think, yeah, at the moment we have actually compared the results from the solid transport module with the MT3D, few field cases and test cases. I would like to test more in the future. I mean, yeah, I hope I answered that question.
Yes, you did. And then another question, is this will be only for just a regular solute transport? There is no density dependent. There is no any kind of simple chemical reaction will be involved also in that module?
At this point, no, it's just the solid transport and particle tracking. Well, in the future, we can definitely incorporate the density dependent features. Yeah.
Okay. So when you mentioned
and everything.
So when you mentioned particle tracking, I'm assuming this is advection, diffusion, dispersion modules, right? It's not only advection.
Yeah, advection, diffusion, yeah, both together, dispersion, yeah, everything included. Yeah.
Okay. Well, thank you very much. I'm excited to see that.
Thank you. Yeah. Well, hopefully, early next year we'll be able to hopefully release that.
Thanks.
Thank you.
All right. Let's move on to our next talk. This is basically from Ali Gaze Minejad, Steve Jepson, and myself from our office. And the topic is the course grid version of the C2VC model, current status, and planned future developments. Ali, go ahead.
Hello, everyone. Can you hear me?
Yes.
Yes, perfect. So, hello, everyone. Thanks for joining. My name is Ali Ghaseminejad. I'm a water resource engineer in the Department of Water Resources. Here, we'll be talking about the current and future state of the C2VSIM course grid version model. Next slide, please. Okay, so first of all, big thank you to all people and group whose work supported this project. Thank you. Next, please. So this the outline of our presentation. What's the current state of C2VSIM course grid model? Our group has been working on a new version, and this version expected to release in few months soon. So in the new version, we updated the major input data set like the historical land use, ET, precipitation, which I will talk about it. We also fully calibrated the model using the PEST. My colleague Steve will talk about it more. And at the end, John will wrap up this presentation talking about the DWR vision for the future of C2VSIM course grid model. Okay, so input So I'll start with the precipitation. Yes. For precipitation, we rely on PRISM 4 kilometer dataset. And for each element of the C2VC model, we extracted the monthly time series data. So there is a wide range of precipitation across the Central Valley. So it's a high around 31 inches in the north side, subregion 1 in the figure in the right, you can see, and around 6.7 inches in subregion 21 in the south. So moving to a small watershed. So as John explained, those are the ungauged small contributing area. And which mostly covered by native vegetation. Since they are ungauged and we don't have information on that, the model use a kind of simple water balance equation to calculate the inflow from those small watersheds. So to be more consistent with the calcium boundaries, we redelineated and reconfigured the setting of this small watershed in this new version of C2VC model. So moving to land use update, we updated the historical land use, and we did it using the fine grid C2VC version 1.5 dataset. The Sigma group did a great job assembled this dataset using multiple sources that you can see the list here. So to bring those information into the core script, we use area weighted averaging method to map the fine grid land use fraction into the coarse grid element based on the intersecting areas. So since the boundary of two models, the fine grid and coarse grid, they are not aligned at some sections, for the coarse grid element that an element is just partially covered by fine grid, we fill it up with a native vegetation. Next, please. So there are some statistics and highlights on land use distribution across major hydrologic region in Central Valley. So we can see that in Sacramento, the native and riparian vegetation make up about half of the land use area. And as we move south into San Joaquin and Tulare Basin, as the climate becomes drier, we can see the native vegetation fraction is lower as land are more developed, and also the fraction of the ponded crop as the climate is drier is decreased as we move from north to the south. I also did another experiment, looked at how that land use acreage varies across different water year types. So overall, the difference are small. In dry and critical years, the agricultural acreages decrease slightly, but it's like that the groundwater pumping worked well as a buffer and allowing farmers to maintain the similar land use pattern even in critical and dry years. So this flowchart shows how we created the reference ET dataset for our model. So in the new IWFM engine, the model receives the reference ET and the crop coefficient as two separate input. So for the reference ET, we start with the PRISM monthly dataset, the minimum and maximum temperature in a 4 kilometer and 4 kilometer grid resolution, and use the Hargreaves-Samman equation to compute the initial reference ET. So in parallel, we also use the special CIMIS data, which is available from 2004 to 2021 to calculate a monthly bias correction factor. What's that factor? We're just simply taking the ratio of CIMIS data, the ratio of monthly CIMIS data to the Hargreaves-Samani estimate, and then use that correction factor to correct our initial estimate from Hargreaves-Samani. And then since the special resolution is 4 kilometer, we aggregate it to the WBA as a water budget area of the calcium model to be more consistent with the calcium. So in a right side, we can see the annual average of reference ET, and we can see that pattern follows the temperature gradient from north to south. Next, please. So as we created the reference ET, so in this flowchart, it's showing how we generated the crop coefficient. To generate the crop coefficient data set for our model, we use the PyCop model to calculate firstly crop evapotranspiration, or ETC. So PyCop is a Python version of the COP model, consumptive use program. It's translate the reference ET to the crop evapotranspiration using different parameters like the crop specific coefficient, growth stage parameter, and many more. So once the daily evapotranspiration is computed using the PyCop, we firstly aggregate it to the monthly ETC because our model received the monthly data. And then also we aggregate the individual crops into the broader crop category that we define in a C2VC model. And finally, by dividing the crop evapotranspiration by reference ET, we calculate the KC, or data set, the crop coefficient data set for our model. So in the right side, we can see the crop evapotranspiration annual average across the Central Valley. So it's not like the reference ET follow an obvious pattern, because it's more affected by a special distribution of multiple crops in a Central Valley. Next, please. So this is a comparison between the actual ET and the potential ET for ag, the figure in the left, and the native vegetation in the right. So for ag, actual ET stay very close to the potential ET. That's because that irrigation supplies the water needed for crop to meet the demand. But the story is different for native vegetation. So native vegetations, they are largely water limited. So actual ET is much lower than the potential ET, especially in dry and critical years. So the other thing that I can highlight here, while the agricultural actual ET remains kind of stable, we can see that they are stable even in a different water year type. That was another observation that we see here. So yeah, that's all from my side. So my colleague Steve will continue from here. Thank you.
Steve, we cannot hear you. Nope. You might want to unplug and replug your headphones.
I wish there was a way to test this before the meeting. I
Yeah,
tried to, but I couldn't figure it out.
Yeah, we can hear you now.
Oh, okay. Okay, thank you. My name is Stephen Jepson, and I'll be talking about the work that we've been doing to calibrate the C2VSIM course grid model using PEST. So we developed a calibration of the different trying to capture all the major components of the model. These include the aquifer and aquitard, the unsaturated zone, stream bed, root zone, and potential ET. And the objective was to minimize model errors across the entire model domain during water years 1984 to 2015. Next. And two sets of observations were used for the calibration. One set shown on the left consisted of water level time series from over 2,600 wells that were screened in a single layer of the C2VSIM model. These wells were selected because they were screened in one single layer, and that was done in order to simplify the process of matching a model layer to an observation. So we don't need to aggregate up heads across multiple model layers into a single value. And as you can see, the wells tend to be clustered along the axis of the Central Valley, with a lot of quite a few bare spots along the western San Joaquin Valley and the most northern region of the model. And the other set of observations consisted of stream flow monthly time series obtained from 27 stream gauges. Those gauges extend down to James Bypass, which is along the North Fork of the Kings River, about 20 miles southwest of Fresno. Next. So there were three key methods of the calibration that we followed. One method was to estimate all parameters in the same calibration run. This was done to include parameter interaction effects. That's where the sensitivity of one type of parameter depends on the value of another type of parameter. Another reason for doing this was to increase the efficiency and reproducibility of the workflow. Another method was to use, whenever possible, baseline parameter fields that were derived from observations and/or literature. These baseline fields provide us with fallback positions for parameters that are relatively insensitive, so that if those parameters don't have very much effect on the model, they can stay where we expect them to be based on observations or the literature, thereby giving us a more appealing parameter distribution. And the third method was to use spatially varying scaling factors that were applied to the baseline parameter values. And those were applied using multiplication, but one could also use addition, subtraction. Next, please. Five system components of the model were calibrated. Those were potential ET, root zone, unsaturated zone, aquifer and aquitard, and stream bed. Those are shown here in the schematic. Each of these components consisted of 1 to 4 parameter groups. For example, the root zone component consisted of, shown on the upper left, consists of 4 parameter groups that control rates of water flow through the root zone and the fraction of precipitation going to runoff. These parameter groups, totaling 13, were distributed across about 63 locations or pilot points in the model, giving us 1,261 adjustable parameters total. Next. We adjusted aquifer parameters in the model using a utility developed by SS Papadopoulos and Associates called Texture to Par. This utility first interpolates data from two different types of sources. One source on the left is sediment texture data from wells. This provides us with information about the heterogeneity of the aquifer in terms of coarse or fine materials. The other source of information shown on the right is the parameters that we are estimating in PEST. These are the hydraulic parameters, the anisotropy of the aquifer. These are defined separately for coarse and fine materials at each of these pilot points shown here, and those are interpolated to the groundwater nodes. And then once we have the PEST parameters and the texture data interpolated to groundwater nodes, we can scale up the hydraulic parameters to bulk values that the C2VSIM model requires. Next. One example of parameter adjustment by scaling is for saturated hydraulic conductivity of the root zone or non-ponded crops. That's shown in the map on the left. Baseline values of saturated hydraulic conductivity were obtained from Surgo databases, extracted using the IWFM Soil Data Builder with GIS tool. These baseline parameter values were multiplied by scaling factors that are the parameters in PEST, and those are shown in the map on the right. Those scaling factors were interpolated to element centroids and then multiplied by the baseline values. Next. So I'll show two slides here of model results. This slide shows streamflow errors at the start and end of the calibration. Stream gauges in the Sacramento Valley are on the top, and gauges in the San Joaquin Valley are on the bottom. Mean absolute errors are on the left, and average residuals, which are observed minus modeled, also known as the bias, is on the right. Mean absolute errors were lowered by about 10,000 acre feet per month in both the Sacramento Valley and San Joaquin Valley. This lowering of error was a larger fraction of the initial error in the San Joaquin Valley, which is on the lower left. So you can see that the calibration produced a higher fractional lowering of error in the San Joaquin Valley. And most of the streamflow bias in the Sacramento Valley, shown on the upper right, was removed by the calibration. About 3/4 of the initial bias was removed. Oops, sorry. Next. And this slide shows groundwater level errors at the start and end of the calibration. Northern wells are shown on the top, and southern wells are shown on the bottom. Mean absolute errors were lowered in the wells in the north by about 10 feet to about 10 feet of error on average. And in the south, the errors were lowered by about 25 feet. So we have much more lowering in the south than the north. And as you can also see, the residual, or the average residual or bias, was lowered by about 25 feet in wells in the south. That's shown on the lower right. So we have much more lowering on average of bias in the south and the north. And you might notice that this is reversed to the stream flows, where we have more lowering of bias in the north than the south. And I think this may have to do with differences in surface water, groundwater connectivity, across gradients, north-south gradients in the model. Next.
All right,
Okay,
I
thank you.
guess. Yeah,
Okay,
sorry, Steve, we have only just a few more minutes left. Thank you, Steve. So this model, actually, we're trying to make it available, before the end of the year. It might, happen in January, but we are very close. So this is basically what we have as far as, what Ali and Steve described. So we have been thinking about future of this model. So if we basically think about the mission of coarse grid C2V Sim. Why do we even have this in the first place? Basically, the main reason why we started, developing C2V Sim almost, 3 decades ago, coarse grid C2V Sim, is to provide hydrologic data to calcium, right? Like in terms of stream groundwater interaction, water demands, land surface flow, so on and so forth. So it's basically works in conjunction with our calcium model, which is a reservoir systems analysis model. We currently link pieces of C2V Sim to calcium, like the groundwater dynamic link library, again to provide stream groundwater interaction to calcium. And in the past, we also tried to link fully to calcium. We have made some presentations in the past in terms of CV-SOM and stuff like that. It was a proof of concept type of approach. Another goal for C2V Sim, not many people have used it so far, but it can be used, is through the multi-model feature of IWFM. It can be linked to local, highly refined models to provide dynamic boundary flows, right? Like boundary conditions are always an issue with these local models. And, one option is to link them to a coarse grid model like C2V Sim to have a, more dynamic groundwater flows between the two models. And of course, we're talking about linking to calcium, we're talking about linking to other models. So we are interested in fast run times, which means that we need to stick with some type of coarse grid. So this is kind of the main reason why we have C2V Sim, or reasons. But when you look at the grid, the current grid, the grid was developed in 1980s. This was before calcium even existed, right? So in terms of like when we want the two models talk to each other, we see lots of inconsistencies, and it kind of makes it difficult for us to make the two models link to each other and talk to each other. So our goal moving forward after this release that we've been talking about today is to basically develop a new generation coarse grid C2V Sim with a new grid and with some new simulation features. So some of the things I want to cover that we want to address with the new gen C2V Sim coarse grid. So here's a picture here. We are looking at the blue or green boundary is the Central Valley groundwater aquifer as described by Bulletin 118. Sorry. Whereas the black line is our current model boundary. You can see that we are actually missing a large part of the boundary here in the Redding Basin in the north. As you go south, you can see here that there's some areas where we are overshooting. So again, this model, the grid, was originally developed in 1980s with the existing technologies. Our understanding of the hydrogeology of Central Valley has been improving. Our technologies in terms of GIS techniques have been improving. So we want to address these inconsistencies between the model and the reality. Another, alignment issues with the streams. Here, the purplish line is the streams as described by the NHD data, and the blue lines are our representation of these streams. So again, we are dealing with a coarse grid model, so we are not going to obviously capture every twist and turn of each of these streams, but we would like to have at least our stream nodes to be on the streams and our confluences right on where the confluences are really occurring in real life. Of course, another goal is to align C2V-SIM and calcium. So basically, we want to make sure that both models are representing the same streams and canals. In terms of alignment of boundaries, here's an example. The colorful polygons are calcium, what they call demand units. You can see that part of the Central Valley is missing for calcium because it's mainly a surface water system model. So we want to address these as well. So it's a mixture of updating C2SIM as well as calcium. I already talked about this, some of the new features that we will need to properly represent reality is again developed small watersheds. I'm not going to delve into it too much. I also talked about fractional surface water deliveries to elements. This is mostly to be consistent with calcium, how the surface water operations are done. But another thing we are thinking about introducing is time series lake outflow. So currently, for instance, this is the Black Butte reservoir. We don't explicitly represent this reservoir as a lake, but historically there's measured releases from this lake into this section of the stream, and currently we struggle to properly simulate those. We have to do some funny business trying to get those historical releases introduced into the model. So we want to actually introduce this what we call time series lake outflows. So that's basically it. I'm going to take one question. We are kind of running out of time. If there's any questions for any of us, any three of us. Okay, great. So let's move on. So next up is Behruz Etebari, again from DWR, from Sigma office. And he's going to be talking about the application of machine learning algorithms, random forest and cluster analysis in determining aquifer hydraulic characteristics based on step, drawdown, pump test data. Go ahead, Behruz.
Good morning, everyone. My name is Behruz Etebari. I'm a senior engineering geologist with the Sustainable Groundwater Management Office. The topic that I'm going to touch on today is the application of machine learning algorithms, like random forest and cluster analysis in determining aquifer hydraulic properties of the Central Valley. Okay, there are updates in regard to C2V-SIM fine grid version 2, and version 2, of course, fine grid model is different than coarse grid. We have nodal spacing is different, and the mesh is finer. But in regards to geology, we decided to change the aquifer layering from 4 layers to 6 layers. And we looked at some USGS reports, and we added 2 layers to the previous model, one to the above Kirkland clay and 1 layer to the bottom of Kirkland clay. And in regards to data expansion, we received a ton of well completion reports, and we decided to incorporate this data into C2V-SIM fine grid version 2. The other thing is our team is actively examining new methods and new approaches to improve the process and results. As you can see here, this is starting 2020 that I joined to the Department of Water Resources. I was told to look at the stratigraphy, geology, number of aquitars in the Central Valley. I realized that there are additional information starting from oil and gas wells or USGS reports and base of fresh water. We looked at the geology. We modified the bottom of aquifer that we done QA/QC with existing GSP reports that were coming from local reports in the Central Valley. And we decided to incorporate these new data sets. And on the left, you see the depths to the bedrock. This is new version that we done like ton of effort to look at like 10,000 wells for base of freshwater, like 5,000 wells for bottom of the Central Valley aquifer. And on the right, on the middle, you see the base of freshwater. On the right, you see the difference between bottom of the C2V fine grid model, new version, and the old version. Incorporating new data from USGS, we realized there are additional occupants like HLA. This one, the blue one from top, we have HLA. The other one, let me see, I can laser pointer. Yeah, this is HLA, as you can see here. This is Corcoran clay. And we asked consultant to look at this data. We shared GIS information. This is base of freshwater that is going to be layer 5, bottom of the layer 5. Bottom of layer 6 would be the new bottom. And these are new occupants that we have added to the Central Valley model, fine grid actually. Going back to the data itself, we received a ton of digitized well completion reports from our consultants, and they looked at PDF files and they digitized or modified location of wells or etc. But if you go to the Department of Water Resources data set on open data, you can see the well completion reports, digitized ones, and there are information there. We decided to make use of this data. How can we benefit from this data? Because there are a ton of informations over there, and they are useful, like total depths of each well, top and bottom of perforations, well yield in gallons per minute, total drawdown, and pump test lengths, and also like static water level at the time of drilling and casing diameter for each well. In this slide, as you can see, it's a paper format of a well completion report in California. On the left, you see information in regard to lithology. On the right, you see well development information like water level, estimated well yield. This one is a pump test. Pump test is different than Baylor test. 2,100 gallons per minute is not a Baylor test. It's a pump test that they lower the pump, they pumped out for like 9 hours, and then they developed the well, and then they reported all of the information into their well completion report. And we don't have, for some of these wells, we have digitized data. For some of them, we don't have digitized data. But total number of 10,000 wells with specific capacity data, depths to the bottom of the well, top and bottom of perforation, are existing for Central Valley. This is a map of Central Valley with pump tests. Short duration pump tests are the black ones, and red ones are existing local pump tests within Central Valley. Short duration pump test comes from the Department of Water Resources well completion reports data sets, and red ones are coming from other agencies like USGS or water districts or GSP reports. As you can see, we have a decent amount of data, and we have a nice distribution and density and population of data. But what are the problems with these wells? Because they're coming from drilling companies, there are problems with data, because sometimes there are typos, and there are problems with estimation of transmissivity or specific capacity. Okay, how can we resolve this issue? I decided to use the cluster analysis, which is going to be an unsupervised machine learning. We can run in Python. I ran this tool, this library, and we could identify those typos or outliers that stands out of the existing data. And we ran the Python code, and now I looked at the data, and okay, those red ones are outliers. In Python, we have like X and Y, specific capacity, and in the code and library, we realize, oh, there are 97 outliers in the data. We have to remove this data because sometimes like 600, the specific capacity of 600 or 0.0001, those are not correct. We ran the code and we could find all of the outliers, and if we remove this data from our data sets. Okay, the techniques that I use to estimate transmissivity, there are two types of methods, like approaches for estimating transmissivity. In this slide, as you can see, we have empirical methods. Empirical methods are different than exact methods, like Rozak and Huntley, 1991, or Mace technique, or Driscoll technique, 1998. They use like empirical equations to use a specific capacity, which is going to be Q over, or pumping rate, or well yield over drawdown. And this is like an empirical equation or scale factor. They use this for 15.3, or in here, 33.6, but for metric units and for US customary units, we have two different equations, and we applied these equations in Python to those data sets. But I realized there are exact equations as well. For example, how can we use Cooper and Jacob methods? Because they may provide better estimates of transmissivity in the Central Valley in California. That's why I decided to look at the literature I found on ActiSolve company. There is an algorithm. They use the successive approximation to solve transmissivity. I decided to use a Nelder-Mead approach, which is going to be an iterative method with an initial guess for a specific for storage coefficient. This term here is called SC, storage coefficient. But as you can see here, we have a well. For some wells, we have just pump tests. We don't have a monitoring well. Some of them are short duration pump tests, and we have just one pump test. But for long duration pump test, this is okay. We have a monitoring well. We can estimate a specific coefficient or specific storage. But for single wells or short duration pump tests, we are unable to use Cooper and Jacob method or other methods. That's why we use the Nelder-Mead approach in Python to automate the process and look through all of the data and estimate transmissivity. Okay, I decided to incorporate more in exact equations because ActiSolve used just Cooper and Jacob, but in the literature there are Streltsova or Bolton or Tice. Tice was developed only for confined aquifers, or Jacob only developed for leaky confined aquifers, or some of them like Moench, they use the different analytical approach to estimate transmissivity and storage coefficient. In regards to skin effect, for each application, they incorporated one additional parameter to the model, and they developed a new model. These are the methods that I use for this analysis. Going to the next slide. Okay, now we have a lot of data, like a lot of estimates. Which one is the best? Which Tice is providing transmissivity only for confined aquifers. Can I use Tice equation for unconfined aquifer in the Central Valley? Okay, below Korkonkole, it's okay to use Tice equation, but above Korkonkole, or in some areas we have leaky aquifers, is it okay to use Tice for above Korkonkole, or is it okay to use Tice equation for leaky aquifers in the Sacramento area? That's why I decided to use machine learning techniques. With machine learning techniques, machine learning techniques like random forest mimics the brain function and looks at the data and creates like a tree of the data that we use like 100 estimators to look at the data And the technique is using all of the information, all of the transmissivities that we estimated from test analysis, like all of the methods that I showed you in the last previous slide, to estimate storage transmissivity and storage coefficient. Okay, what steps I took to analyze this data? First of all, there are missing data. Sometimes we have to fill those data gaps. We used K and N imputation for missing data because sometimes the method fails to run the model and estimate transmissivity. We have, for example, for Newman, for 7,000 wells, like we have 5,000 estimates. But Batu is it's not an exact equation. It's like an empirical equation. It doesn't fail. We have a lot of estimates for transmissivity, like 7,500 wells. For all of them, we have transmissivity data. Okay, how can we fill those missing transmissivities that our Python code failed to estimate transmissivity? We ran by using SciPy, we used KNN. For random forest, we follow those steps. First of all, it's creating a synthetic estimate of transmissivity data based upon the median of estimates. Then, because random forest is kind of a supervised technique, it is using regression equations to look at the construction information, geospatial like coordinates, geospatial information of each well, and it's looking at the hydrology or hydrogeology, like top and bottom of perforation or etc., and transmissivity estimates. But random forest requires training. It looks at, like, we define like 80 like value for training the model, and for testing, like it's a ratio of 80 to 20 for testing and training the model. And it is using, you can use other techniques, but we use random forest regression. Number of estimates like 100 trees, and it is going, the Python code runs the random forest technique, and the model estimates transmissivity based upon whatever technique that you think that is the best technique for estimating transmissivity in the Central Valley. Okay, I decided to use Newman technique. Okay. Now, we ran machine learning, but what are the statistical analysis of these methods? These are like Newman, Rozak, MACE, which is like a technique for fracture aquifers, or the other one is Streltsova, or Moench, or Badu. We can look at this statistical distribution of data, or sometimes there are overestimations, sometimes, oh, this is not quite correct. We have underestimation of its transmissivity, or for some of them, they are going above, like here, like Jacob. We have a lot of underestimation for these techniques. But averaging is not the accurate way to like finding the transmissivity, best transmissivity for data. That's why we use random forest. And now we have an optimized transmissivity for Central Valley. Okay, now look at the transmissivity data. We subdivide the transmissivity over saturated thickness of the aquifer. Saturated thickness comes from top and bottom of perforations, or sometimes water level and bottom of the drilled well information. And okay, now again, look at cluster analysis and run the code with hierarchical conductivity. We could identify additional 100 data that doesn't follow the general pattern of the Central Valley. For those wells, like top and bottom of perforation are really like, there are errors or typos. And once you subdivide transmissivity over the saturated thickness, oh, it's an overestimation again. We use the cluster analysis and we remove those bad data. This is the Python like squared score, and mean square error for the Central Valley. As you can see here, data, for example, here we have for these, these are the top, first top estimates of transmissivity for each method, like Driscoll, Jacob, Hantush, Papadopoulos, and etc. This estimate is 68, this is 94, this one is 95, 72 for higher transmissivity, 50. What's the best estimate for optimized transmissivity is going to be 70 square feet per day for transmissivity and etc. This is the distribution of data for those zones. Because we subdivided all of the data sets in we subdivided Central Valley into 6 layers. Some of them follow the geology, some of them are not following the geology. That's why we call it layer 1, 2, 3, 4, 5, 6, which is going to be like a layer cake model. But in some portion of the Central Valley, it follows the geology. In some portion, it's just zonation. But for each well, we have quite a decent amount of data for layer 2, layer 3, layer 4, and layer 5. For layer 1 and layer 6, we don't have enough information because top and bottom of perforations sometimes begin below layer 1. We have decent amount of data for layers 2, 3, 4, 5, not 6. But we have enough information for Central Valley. And as you can see, I showed you in the previous slide, since we don't have enough information for layer 1, it's quite obvious that, there are, because we use Kriging method to estimate transmissivity here. Here we see, there are not quite, it's not quite accurate to use this data set. But for layer 2, we use the Kriging method, empirical Bayesian Kriging, and we run it, and we have transmissivity for layer 2, layer 3, layer 4, layer 5, layer 6. Those are just layers that follow the geology or zonations. We subdivide the transmissivity by the saturated thickness when we have hydraulic conductivity for layer 1, 2, 3, 4, 5, 6, and min-max is, as you can see here, like 1 feet per day to 145, 1 feet per day to 175, 1 feet per day to 106, 1 feet per day to 147. Here, less than 1 feet per day to 75 feet per day, and here 51 feet per day max. As you can see here, as we go down to the deeper layer, the hydraulic conductivity is decreasing, and I'm happy. Okay, this is good. What about the specific yield data sets? Specific yield data sets are useful as part of the C2V fine grid or IWFM model, because for some of them we use the short duration pump test. As you can see, layer 6 is not quite, because we don't have decent amount of data, but layer 2, 3, 4, 5 are showing better distribution, and it looks like, yeah, as you can see here towards the edges of the model, we have less than 2% of specific yield. Towards the Bay Delta, it's lower than areas that we have more wells. Going to the next slide, this is a specific storage, because some of the pump tests are coming from long duration pump tests very close to Chico area or Yuba City. We have higher estimates. That's why we see some bullseyes here. But to me, because specific storage times to the exponential exponent of -6, those are values actually here that for some of them I use the it shows +2, but we have to multiply by exponent of -10 to the power of -6. But variation of the storage coefficient it's not very similar to hydraulic conductivity, because hydraulic conductivity values is changing maybe 2 or 3 orders of magnitude, but for a storage coefficient and specific yield should be 1 order of magnitude. And the other, the last component of the aquifer parameters is storage coefficient. For layer 6, as you can see, we don't have enough data here, but for other data, some bullseyes, but we can refine it later, or we can look at below Corcoran-Clay here for estimates of storage coefficient using Theis method, not using Newman method. Okay, what's going to be the statistical analysis of the data? As you can see here, I used the Python to look at the mean, max, and standard deviation of all of the parameters in the Central Valley to see, okay, like min max looks good, mean average of layer 1, like 30, 6, 30, 27. This is for highlight conductivity. As we can see here, going down to the deeper layer, we have 6 feet per day. We have here 31, 32 feet per day average. It's not like 1,000 or 10,000 feet per day of data. Okay, it looks good to me for storage coefficient and storage other parameters. And thank you so much. Back to you, John Duggar, Dr. John Duggar. If you have any question, please. Okay.
Yes, Mohammed.
Yes, hey, thank you for the presentation. Actually, I have 3 questions, but I think will be very quick. First, did you publish this work in any peer-reviewed journal?
No, I haven't, but I received an email from the Dr. Tariq. He mentioned we have a presentation in QAMF in regards to machine learning in water application of machine learning in water resources. Would you like to join our group? I said yes. Okay, but we're gonna present it to the broader audience, maybe in April.
And QAMF, that's in 2026, I think in April or March, right? Okay.
Yes, April.
And then the second question, is there a public accessibility for all of those pumping this data after you filter them and you remove all of those outliers? Do you have this data accessible to the public?
I haven't I haven't shared these data sets publicly, just with the consultant company. We share this data set internally, but I don't know because I have to use them. I have to ask. But we will be publishing these data sets maybe in 2026 once we with version 2. Yes, with version 2, but it's going to take a while.
Okay, and then the last question about the specific yield. So I noticed you have those specific yield for the deeper layers.
Yes.
I don't know how you get the specific yield for the deepening layer. I know it's by interpolation or extrapolation, but I don't think there is a data can support that. That's number 1. Number 2, I'm wondering why the specific yield is larger than 1.
It's percent. It's like a percent. We have to subdivide by 100. Yes.
Oh, okay.
Sorry, I put here no values, but it's for C2V fine grain IWFM. It's going to be like
sure.
0.15. Sorry.
All right, that makes sense.
It's coefficient actually. Yeah.
Okay.
Sorry.
Right.
I will fix it for QAMF.
All right. Thank you.
Thanks for your question.
Thank you, guys. Thank you, Behruz. In consideration of the time, we're gonna move on. We're only 7 minutes behind schedule at this point. Our next presentation is from Wouterden Curran, Ahmed Ali, and Adrian Camille, and they will be talking about IWFM FV, a Python tool for visualizing groundwater flow. Ahmed, Adrian, go ahead, share your screen and take it over. Adrian, you are muted if you're talking.
Thank you so much. All right, my name is Adrian, and together with Ahmed, we will be presenting IWFM FV, which is a Python tool that was developed for visualizing groundwater flow directions. So the objective of this tool was to provide a very quick and efficient way to visualize groundwater flow direction vectors from IWFM models. And in lieu of having access to a tool like TechPlot or having not output the flow velocity output from IWFM, this was just sort of an efficient way to generate that output for multiple models at a time. And the point of this was to evaluate impacts on project pumping and how that affects groundwater flow directions and could potentially have implications for contaminant movement. And part of this tool that we'll discuss later was to be able to contrast a baseline versus a project scenario and how those project scenarios affected the groundwater flow direction and flag what we could consider significant direction changes in groundwater flow. And this tool exports GIS ready layers like shapefiles and TIFFs, as well as some PNG figures and an animated flow direction throughout the model time period. So the basic inputs for this are, your IWFM nodes and elements, and then the output from the model, which is just the groundwater head data by node. And then a few things that the user can actually specify is the target month if you're looking at just a specific month and year in the model. And then we also have a part of this tool that exports groundwater head contours, which is just for verification. So it's nice to see those flow directions on top of those head contours. So you can specify the groundwater head contour interval that you would like in there. And then whatever you would like to consider a significant threshold for the angle direction changes if you're comparing between baseline and scenario. So, if you would like to see which elements there was a change greater than 10 degrees in groundwater flow between baseline and scenario, you could specify that here. So the general workflow for this tool is you take those inputs that I talked about in the last slide with those head values, and we have the gradient is calculated, which Ahmed is going to talk about a bit more in detail next. And then it generates those flow vectors and all of those outputs that we've talked about. So next I will pass it to Ahmed to give a little bit more detail on the technical side of things.
Thank you, Adrian. My name is Ahmed Ali. On this side, I'm explaining how the code converts nodal head values into flow direction vectors at the element scale. We start by assuming that within a single element, we had the head very smoothly enough that can be approximated as shown on the slide. Hxy equal to a multiplied by x plus b multiplied by y plus c. A is the head slope in the x direction, b is the slope in the y direction, and c is the constant offset, the intercept. Now for each node in the element, we know its coordinate x and y and its simulated head h. So for each node, we can write one equation as this shown on the slide. H equal to a multiplied by x plus b multiplied by y plus c. If I stack all those node equations together, that becomes the matrix form shown on the slide, matrix A. So here what we have, as shown on the slide, H is the column vector of the observed nodal heads from IWFM model outputs. B is a known coefficient vector we want to solve for. As shown on the slide, we have A, B, C, unknown values, and A is the matrix built from node. So each row is representing per node, and what we have in the matrix, we have x, y, and y, and 1. The one is how the matrix includes the constant term c. It's equivalent to writing h equal to a multiplied by x plus b multiplied by c plus c multiplied by 1. So the one is what allows the solution to find the best intercept, the vertical shift of the plane. If we didn't include that column, we would force c to equal to 0. And also in most elements, we have more than 3 nodes. We have more equation than unknowns, so the system is overdetermined. That's why we use a least square solution. we don't try to match every node perfectly. We want to find the plane that best fits all the nodes in the element. The other parts are shown on the slide. We have ABC. So once we have the plane coefficients, we compute the head gradients for xy equal to a multiplied by x plus b multiplied by y plus c, as shown on the slides. Then the partial derivatives are a change of head with respect to x equal to a and change of head with respect to y equal to b. So the gradient head equal to a and b. The gradient points toward increasing head, but groundwater flow from high to low head, downgraded. So we reverse the direction as shown on this line. And if we wanted to calculate actual discharge, we would use Darcy's law, as shown at the bottom of the slides. But for this code, mainly we want direction. So we normalize to a unit vector. As shown on the slide, unit vector equal to change delta head divided by the magnitude of the gradient of the head. So for every element ends up, we have ux and uy as the unit direction component, as shown on the figure. So usually the workflow is to that we gather nodes per elements. We build a matrix. We solve for coefficients A, B, C by least square. Then we compute normalize it unit vector. We write those arrows as a vector shapefile and float them over the contours. Next slide, please. So in the code, we have different outputs. For example, we have flow vectors as shapefile. As earlier mentioned, we have specific criteria if we want to measure the significant change. So we have a separate shapefile. Also, we have head contours shapefile, as also we have PNG if you want to quickly visualize it. Also, we had heat difference contours shapefile and PNG. Next slide, please. So here in this slide, we have two examples. We have here groundwater flow direction for the baseline on the left, and we have another one for the CR. So in the code, we have options to define the baseline and different scenarios. So the code will go and read for baseline scenarios. Then we have a separate shapefile for the baseline, also separate shapefiles with all outputs for each scenario. Next slide, please. Also, we have shapefiles for the baseline and scenario, so we can open both shapefile and see how what's the groundwater flow direction in the baseline compared to a scenario. So as shown on the slide, we have the below arrows for the scenario model and the black for the baseline model, and we can see how the scenario impacting the groundwater flow reduction in the baseline, and we can see the effect. Next slide, please. However, if we want to see where we have the significant change, and in our criteria, for example, in this code or example, it's 10 degrees, so we can show only the elements with a significant change. So if we want to just focus on where we have a change and we don't want shapefile to be crowded with all arrows elements, so we can show only show elements with a significant change. And our criteria, as Adrian mentioned, it's 10 degrees, and it's up to user. It can be 2, 3, but in our case, we use it 10 for this example. Next slide, please. And also in the code outputs, we have head contour shapefile for baseline, scenario, and difference between baseline and scenario. So we can use this with the shapefiles for the groundwater flow arrows as reference background, and we compare how the groundwater flow is moving. And we can see also based on the contour lines. So this is like additional outputs, and we can use it as a reference also. Next slide, please. So also in the code outputs, we have animated versions. So for example, here we can see arrows with a defined significant change in the flow direction is in blue. And in this example, we are using the criteria 2 degree, and also arrows with no significant change in the flow direction in green. So we can see below arrows are changing over time, and it's up to user to define the time frame. For example, in this example, it goes from 1970 till 2020 or 2022, and we can see how the groundwater flow arrows are changing over time. And this is just a random example, but it's up to user to define the specific area or to examine which part of the model. And back to Eddie.
Great, thank you. So as a just quick summary, this was a tool that was created to generate flow vectors, but meant to be simple, quick, and efficient, and be able to handle scenarios and baselines for comparison. And it creates those flow vectors for each element, and then is able to map those head differences and identify what you have decided as a significant change in flow direction. We've made sure that it outputs in GIS, PNGs, and that animated GIF. And then we know that this is, has a lot more that could be built on top of it. So we have a few future plans that would help in our personal project uses, which is working on streamlines and plan view. So having continuous flow paths instead of just the head gradients or that arrow per element. And then multi-layer support. So instead of the way it's handling layers right now, just handle heads per layer. So we could look at how the flow velocities, flow directions change in layer 1 versus layer 5, or depending on whatever model you have. So you could really just look at specific aquifers or aquitards. And then looking at cross-section flow plots. So looking more at the flow directions in vertical cross sections, and have a comparison of the horizontal versus vertical flow directions, and maybe how that also is changed between baselines and scenarios. So with that, that is our quick presentation, and yeah, back to you, John.
Thank you, Adrian and Ahmed. I actually have a question. Like direct application of Darcy's equation and taking the gradient of heads that are coming from finite element method are basically, if you do that, you end up with mass balance equations, right? Like, one of the things is if you do that, you end up with locally your approach. I mean, the numbers that come out are not locally mass conserving. So in IWFM, we went to great lengths to basically go around it and make sure that the velocities that we calculate are mass conserving. Is there a reason why you are not using those velocities that are coming from IWFM and essentially kind of, using the Darcy equation directly?
Yeah, so this was really built out of, we had a lot of models that were run, and we had never exported that velocity output, and we just wanted a very simple general visualization of the flow direction, not necessarily the velocity. And so in lieu of having to rerun all of those models with that output, this was created just as, a reference to understand how our baselines or our scenarios are changing the direction shifts from the baseline based on the scenario pumping. So, I guess it should be also part of our future plans is to incorporate that velocity output specifically from IWFM, and maybe, run those scenarios with the output all the time.
Yeah, just wanted to put the caution out there. Yeah. Any other questions? Yes, Maysam.
Hello, Mason from LSC. We know that Python is the interpreted language model, and we know that C++ is faster in terms of visualization. How fast is the code you developed compared to other visualization tools? And especially if you want to add cross sections in the future, maybe that would be more important. Yeah, thanks.
Yeah, actually, for this, we use Python, and it's like it takes like maybe 10 minutes if you want to run for a specific date, like let's say like September 2021. So it will take around maybe 10 minutes or 7 minutes. But if you want the animated version for each time step, it will take like 1 hour to, for example, to have animated version for like 20 years. But if for a specific date or like 2 or 3 years, it's good. But yeah, maybe in the future, if we want to develop it, maybe we can use other language. maybe they will be faster than what we have right now.
Thank you.
Yes, any other questions for Ahmed and Adrian? All right, great. Thank you both. Let's move on to our next presenter from UC Davis, Yara Passner. And the title of the presentation is Vertical Hydraulic Gradients as a Diagnostic Tool, Insights from CVHM2, C2VSIM FG, and SVSIM in the Sacramento Valley. Go ahead, Yara. And you're muted, by the way.
All right. Can y'all hear me?
Yes, and we can see.
And you can see the screen?
Yes.
Do you see my slides?
Yes.
All right, we're in action then. Oh, I can't see any of your faces, but that's okay. So hi, my name is Yara Passner. I just defended my PhD at UC Davis, so I guess I'm a recent doctorate student of the Hydraulic Sciences graduate group. And today I'm going to be talking about vertical hydraulic gradients. So that talk previously was a really great setup because we talked a lot about horizontal gradients and how vertical gradients maybe are on the horizon. And so today I'm going to talk about what those vertical gradients look like in each of these models and how they can help us diagnose these models, perhaps in improving their accuracy. This work is in collaboration with my dissertation committee, which includes professors Helen Delka, Graham Fogg, and Thomas Harder. All right, let's get into it. So pretty much just introduce myself. I have a background in math, and I'm from UC Davis. This is the definition of the hydraulic gradient. So it's technically the vertical component of the head gradient vector. And this is how we typically measure them. So with multi-level monitoring well nests, where one specific location has multiple vertically differentiated head signals, and we can differentiate those to understand the flow direction, like we just talked about, where you can see positive gradients in my scheme are going to lead to downward flow, where the head is dropping with depth. Negative gradients are upward flow. And then the other big term that we're going to talk about a lot today that motivates this research is the definition of vertical anisotropy, which was also mentioned earlier. So that's the ratio of the horizontal K to the vertical K. In the models that we're talking about today, these are kind of upscaled values. So they're upscaled to the model layer. So when I refer to vertical anisotropy, that's the value I'm referring to. And the motivation for this talk is a meta-analysis of groundwater models that came out last year in 2024. This consultant up in Ontario looked at about 300 models developed over the past 30 years. And he noticed there was this significant bias, and it was across model types, across hydrostratigraphy. So here I'm showing when the models had vertical length scales that were greater than or equal to 10 meters. So kind of talking about the models like C2VSIM and SVSIM. There's this bias towards underestimating the vertical anisotropy. And in particular, we can see that the observed data, there's about less than half of model layers in the field studies had an anisotropy of 10 or less. In the simulated data, we see that about 80% of models have an anisotropy of 10 or less. And specifically, 60% of observed models, or 60% of studied models, have an anisotropy of exactly 1 or 10. So this is kind of an overlooked value. And they suggest vertical gradients, and considering them during calibration can really help with this. So that's our research objective, is to kind of explore how vertical gradients, interpreting them during aquifer parameterization, changes the vertical anisotropy and how that has cascading effects on key model outcomes. Getting into our methods briefly, I'm going to be looking at the Sacramento Valley today. It's the top third of the Central Valley. It's a clastic sedimentary aquifer system. There are no clear laterally explicit aquitard layers here, but there is interbedded coarse and fine kind of everywhere. This is a regionally significant system with lots of surface water exports. And it also has a lot of observation data. So in particular, there are 80 continuously monitored well nests that overlap with each of the model domains that we studied today. These well nests had typically between 3 and 5 screen interval lengths that were usually between 4 and 12 meters long, so pretty short, relatively speaking, and had at least 10 years of record at about 80% of well nest locations. So there's like a lot of data, multi-level head data in the Sacramento Valley. We're going to be intercomparing these three models discussed here. So we have the USGS model, CVHM2, which was published last year. I'll be analyzing the C2VSIM fine grid version 1.5 model here in this analysis. I'll be showing those updated results and comparing that to the SVSIM model from 2021. The SVSIM model is special because it's the only model here that actually calibrated its aquifer parameters using vertically differentiated head from these continuously monitored wellness data. So by comparing these three models together, we can see what changed between SVSIM and these other two, which are calibrated otherwise relatively similarly. This is how we matched the observed data to the simulated data. We used the IWFM hideout executable to simulate, we used the model to simulate the head at every single wellness location laterally. And then we extracted all of the layers at each wellness location and did a depth matched approach. So the shallowest observed screen was matched with the shell and with a cell, and we call that the shallow head time series, both simulated and observed. We did the same with the deep one. And we also looked at each screen pair and computed the vertical gradients between those screen pairs. So getting into the results, I'm going to talk about time series at a specific wellness location, just to kind of typify the behavior. This wellness is pretty typical of what we see. It's located in Colusa County, Butte Basin, just north of the Sutter Buttes. This is the observed time series trend, and I'm going to take a little bit to talk about this data because I feel like it's unfamiliar to look at multi-level vertically differentiated head. So what we see here to start is in the dry years, we see significant drawdown in the shallow layers, or in the deeper layers, more so than the shallow, as expected. We see vertical equilibration in wet years and wet seasons. So the deep time series, the deep head series is able to equilibrate all the way up or above the shallow. Looking at the vertical gradient data, the first thing I want to point out is in those drought seasons, in those dry seasons, or drought years, dry seasons, the vertical stress distribution creates the vertical gradients to increase in magnitude, both positive and negative. So there's upward and downward flux. I'll point out this negative 103 meters above sea level time series. It's the second from the bottom. It's not the deepest. And this depth probably shows most of the stress. And so during stress seasons, it pulls from above and below the head signal. The other thing I want to point out is there's an increasing trend in the top to bottom vertical gradients. So generally the deep time series is decreasing faster than the shallow one. And we see this at 52 out of 80 well nests. And in this particular case, we haven't seen the head fully equilibrate at this well nest in like 5 years. And it used to do that every year. So this is a difference. Okay, finally we'll get into simulated data. Thanks all for putting up with the theory. I'm going to start with the SVSIM time series model, the one that was calibrated using this vertically differentiated head. And we noticed that it does a pretty good job. It captures the picture. It captures the heartbeat of the system in the vertical exchanges of the positive and the negative flux distribution. It doesn't capture the extreme values. This might be cell discretization or how the elastic storage is simulated, or the delayed responses. But overall, it captures the picture. Looking at the C2VSIM model, it generally fails to capture the vertical differences through time and through space. So generally, C2VSIM behaves kind of like one mega layer. There's not a lot of differences from top to bottom. So there are differences through time, but those differences are reflected evenly in the shallow and the deep ones. And this is an overwhelming signal. I was unable to find more than a handful of counter examples. In CVHM2, it's a very similar story. The vertical head is pretty much the same throughout all of the different layers, which is an interesting result because CVHM2 is much more vertically refined. It has, I believe, 11 layers. In the Sacramento Valley, it has 9 active layers. So this is an interesting result that the head is still vertically equilibrated across its depth intervals. This is true at about 75% of wells for the CVHM2 model. It does a bit of a better job on the west side of the basin. Getting into spatial trends. So here is the vertical gradient computed at every node in the Sacramento Valley portion of these models. In the CVHM2 model, I'm showing the cells. In the IWFM models, I'm showing the nodes, or the values at the nodes. And these are really pretty strikingly different values. This vertical gradient is the top to the bottom. So from layer 1 to the bottom active layer, as shown in the title here. The C2VSIM model generally, which is shown in the middle, there's a lot of blue. There's a lot of upward flux across the depth of the domain. The SVSIM model is maybe more of the conceptual model we'd expect. So the one on the right is generally in condition of recharge across the basin with discharge or upwelling conditions along the center. Of course, this isn't actually talking about the water table to the stream gauge. So this isn't true upwelling, but this is showing the vertical flow direction across the full interval of the domain. And then the CVHM2 model just has a totally different vertical gradient signal. It's mostly showing small magnitude gradients on the east, and it has more of a heartbeat on the west side. This is a really traditional model performance, scatter plot of head. I separated the shallow time series are in blue and the deep time series in red. While all of them have a pretty good, they have an acceptable statistical fit of greater than 0.97. The slopes are pretty much plus or minus 0.1. There is a significant overestimation of the deep head time the deep head series in both CVHM2 and the C2VSIM model. And this might reflect the vertical gradients being very small magnitude. The shallow and the deep heads are very similar. And so that would mean that the deep head is missing a lot of the natural variation that's observed in the data. But otherwise, this model is capturing, all models capture shallow and deep head in a statistically appropriate way. Where things fall apart is when you look at the vertical gradients, which is totally expected. The SVSIM model was calibrated to these vertical gradients, and it does the best job. That's shown on the right. It has a R value of 0.6, so it's a moderate match, and its slope is positive slope of 0.4, so overall a moderate statistical fit. The CVHM2 and the C2VSIM models both reflect what we are seeing in the spatial chains, the spatial trends, and in the time series trends, which is essentially there's a lot of simulated values very close to zero. And so what we see is a flat line essentially at zero of simulated values with a very poor fit to the observed data. This is caused by the anisotropy differences in the model. Probably, I'm almost completely confident. So when calibrating to the vertically differentiated head, it increased the vertical anisotropy in the SVSIM model. The model developers at SSPNA also noted that this tightened the bounds, the uncertainty intervals around the hydraulic conductivity values. So this SVSIM distribution shift to the right, higher anisotropy by 1 or 2 orders of magnitude, also yielded a more accurate fit. So there was the data, including vertically differentiated head, and the calibration yielded more accurate model parameters and a higher overall anisotropy. I want to show some of the spatial distributions of how these aquifer parameters changed. So I'm defining a metric here, which is effective nodal vertical hydraulic conductivity. A depth or a thickness, layer thickness weighted harmonic mean. And this is the spatial distribution of that effective hydraulic conductivity. So totally different patterns. Overall, we see the CVHM2 model has the greatest vertical hydraulic conductivity, and it is especially large on the eastern part of the basin, which reflects where all the vertical gradients are also really small magnitude. In the C2VSIM model, we see mostly high vertical K through the central valley of the Sacramento Valley, right where the streams are. So there's a high vertical effective K through the center of the valley, where there's also an negative, so upward flowing vertical gradients. And then the SVSIM, we see the vertical gradient, or the vertical hydraulic conductivity is a lot smaller than the other two models, and it's a lot more dispersed, less of a trend. I'm going to get into the groundwater budget. This is my last set of results here. The pumping between these three models is pretty much similar. The monthly trends look about the same. There's only a gap of about 30% between SVSIM and CVHM2, which isn't a huge amount of uncertainty. The CVHM2 model, when we look at the total recharge in each of these models, I want to point out two things. One is that on the left, we see that the CVHM2 model, which is shown in purple, has much larger monthly recharge fluxes, so it's much more variable. This might reflect having a larger vertical hydraulic conductivity, as once the recharge meets the surface, it just very rapidly moves through the system. And then on the right, the C2V-SIM model has a significantly greater total recharge than the other two models do. The last part of the groundwater budget that I want to point out is the groundwater exchange. This has been corrected, and so I'm using the C2V-SIM version 1.5, which thank you for pointing out to me, Guabo. I'm sorry if I'm saying your name wrong. Guibao. Anyway, I'm sorry. Thank you so much for pointing out to me that the effect of tile drains is very, very different in the updated model. So I removed that effect to try and give a fair comparison. So here I'm showing the surface groundwater exchanges between the three models. The C2V-SIM and the SV-SIM model have pretty comparable cumulative exchanges. But if you look at the monthly exchanges, we see it's much spikier in the C2V-SIM model than SV-SIM. So there's more monthly exchange fluxes. And then we look on the right side, CVHM2 shows significantly more discharge to streams than the other two models. So the key point of this slide is that the hydraulic conductivity differences and the changes in vertical gradients probably directly influences this result of CVHM2 showing greater total discharge to streams and greater monthly fluxes in the C2V-SIM model. And they also result in cumulative budget changes. This is mostly probably driven by the difference in recharge, where C2V-SIM shows more recharge than the other models, so it shows less groundwater storage depletion. So some really quick key takeaways. All models do a reasonable job of simulating laterally distributed head, but only SV-SIM captures those trends in vertical gradients. And this model shows a much larger anisotropy and a different groundwater budget and surface groundwater interaction than the other two models do. Briefly, I want to talk about why the anisotropy is simulated here, even though there are no aquitard layers. It's because this is an interbedded system. So I'm kind of showing a conceptual model on the left of what the system might look like, of ubiquitous clay layers and silt with laterally deposited and laterally elongated sand and gravel. When you try and capture these like interbedded vertical exchanges in a single model layer, that means each model needs to be able to facilitate more horizontal flux than vertical flux through it. And this is maybe more of an issue in the Sacramento Valley than in the southern part of the valley, because in the southern part, we're explicitly simulating that Cochrane clay. So there's anisotropy baked into that simulation. But in the northern part, there's no anisotropy. And to be clear, in the southern part of the valley, there is ample justification to think that there should be anisotropy between the Cochrane clay layers as well. So that's something that maybe we should consider. Management implications. The fact that SV-SIM shows that things are very vertically anisotropic also shows things are laterally connected. Their stream depletion report showed that pumping from miles away from the stream affects the stream. The observed increase in the top to bottom vertical gradients through time is not well reflected in any of the three models. And it also could show that the surface water condition, which is currently gaining, could potentially change through time if we continue to have deep groundwater depletion. Some further research is to look at including these vertical gradients in the C2V-SIM aquifer parameterization, specifically looking at it in the Southern Valley, like I talked about. And then there's the role of vertical discretization on how that might change these vertical gradient simulations. So I'm very curious to see what the vertical gradients look like in the C2V-SIM version 2 model with 6 layers. And of course, how does all of this influence transport modeling? So thinking about those flow fields, each of these have totally different vertical effective flow fields. And so if you're trying to use these for transport modeling, they're going to give you a totally different vertical result. So trying to consider how we can include vertical gradients to improve some of the transport simulation results from these models is important as well. I'd like to acknowledge my advisors again. If who pushed me through all the way through this dissertation. Thank you. And technical support. There's a lot of people even in this crowd who have offered your time and expertise to correct my oversights and make sure I'm presenting things accurately in an irrelevant way. So thank you all so much for your help. And I really would welcome any questions.
Thank you, Yara. This is great. Before Mohammed, I'm gonna ask a question. So this is great presentation. I'll have to go back and watch the recording again and maybe contact you back. But so if I understand you correctly, you're saying that one reason why SVSIM has better, more realistic anisotropy, I guess, is because they actively incorporated those 80 whatever vertical or multi-completion wells, or because they have I can't remember, 9 layers, something like that, compared to 4 layers, or is it a combination of both of these factors?
I have to think that it's got to be including the vertically differentiated head into the calibration, because when we look at this plot, are you still seeing my slide?
Yes. Yes.
So when we look at this plot, this is vertically averaged over all of the layers. So I really tried to do an apples to apples comparison here. And we this is noted in the model documentation. I don't know if Vivek is here right now, but yeah, once the vertical gradient or the vertically differentiated head targets were included in calibration, the anisotropy increased. It pushed the vertical conductivity down, and it even pushed the horizontal conductivity up. So it really did separate those two values for this effect to happen.
Got it. Thank you. Mohammed?
Hey, thank you. Thank you, Yara, and congratulations for your PhD degree. It's a really follow-up question, the same question like John. So first, I wanted to confirm: did you recalibrate SVSIM considering the vertical gradient, or you did not?
I did not.
Okay.
This model already was calibrated to vertically differentiated heads, so I just compared their outputs.
Okay. So I just want to add, you know more than me in those 3 models, specifically in that topic of the vertical gradient. But I think comparing, the surface water groundwater interaction, or what you call SW exchange, between the 3 platform or 3 models, it also has an effect on those numbers, because I think different surface water infrastructure, right? Different riverbed properties. I mean, there's a different parameter can contribute to that, not necessarily only the vertical gradient, right? There is too much to compare with. Just I want to add this. But
yeah,
this is... Go ahead.
Sorry, go ahead. I totally agree with you. I had a long conversation actually with my advising committee about this, about how to talk about these models in comparison with each other. And in particular, I would say comparing the C2VSIM version 1.01 model. So this is the 1.5 that I'm showing here. But the SVSIM and the C2VSIM models are using the same lithology data. They're using the same aquifer parameters. Really, the only differences are in the land use. And so I totally agree. And we do see some significant changes in the surface water exchanges that I can't and I have needed to redact from my story. Like, for example, pumping, like the difference in pumping that we see here, I don't think this has anything to do with the aquifer parameterization.
Okay.
But this is very significant, looking at the composition of the groundwater and the aquifer, or of the actual vertical hydraulic conductivity and the vertically differentiated head. I mean, that's kind of what we were trying to tell most of the story on. This is mostly a little bit of a novel contribution to try and seem like what I think one justification here, specifically in the surface groundwater exchanges, is that we can't really measure these fluxes.
Right.
And when a lot of these models, I think all of these models similarly will hardwire in the stage and treat streams kind of like a constant head boundary. And that's, I think, my justification here is we're seeing really spiky interactions monthly. And I think that's a constant head boundary effect of when you have all of the heads are very, very similar from shallow to deep, and all of the heads are also very close to the stream. Then when there's differences, you're going to see a significant flux. All of the layers are contributing their flux upward, and then all the layers are contributing their flux downward. So that is something that I believe is driven by the aquifer parameterization.
Okay, and I saw one point, like you said, for future exploration. You talk about the vertical discretization.
Mhm.
Just like for your information, even for considering exploratory run with constant hydraulic conductivity, okay, 1 kH equal kV equal kz, the vertical discretization, specifically near the surface water infrastructure, have a really big effect in the leakage or the stream water exchange, which is, it's very important, to have a vertical discretization, not necessarily only to define the hydrogeologic unit, but the vertical discretization near the stream has a really big effect to quantify the surface water groundwater, exchange. But again, congratulations for your PhD.
Thank you. Yeah, thank you for those comments.
Great. Any other questions for Yara? All right. Well, thank you, Yara. And we're going to go to our last presentation from Girgos from UC Davis. And he'll be talking about ICNOS or ICHNOS. We'll see which one is correct when he starts talking about it. It's a particle tracking tool for IWFM and beyond. Go ahead, Girgos. We can see your screen, but you're there we go.
Okay, can you hear me now?
Yes.
Okay, is this in the middle or no? No, you can see just the screen, right?
Yeah, we are able to see your presentation, yes.
All right, okay, great. Okay, thank you very much for the introduction, and thanks for the opportunity here. My name is Georgios Kourakos, and I'm going to present ICHNOS. This is a CH is called as he, I don't know how, ICHNOS, which is a particle tracking tool for IWFM, and not only actually. Our motivation was actually to use the ICHNOS for other codes as well. And this is a project that we have been developing with Helen Dahlke and Thomas Harter for quite some time. So in this user group, I believe it's needless to say that particle tracking is a very useful. It's a very useful post-processing method, right? We already saw in the previous presentation actually the usefulness of that. You can, with particle tracking, you can visualize the flow patterns. You can actually delineate capture zones, or you can even do contaminant transport and calculate groundwater aids and more. So particle tracking requires a three-dimensional velocity fields that covers pretty much the study domain, and usually this kind of velocity field comes usually from groundwater flow simulation codes. And because particle tracking is a very common post-processing method, all standard groundwater numerical codes have actually an associated particle tracking utility, like ModFlow has ModPath, and essentially all of ModFlow variants have an associated particle tracking utility. ParFlow has SLIM, and IGSM, which is a predecessor of IWFM. I found a list in reference that there was actually IGSM PT, which probably stands for particle tracking, but I was never able to find the code for that. But yeah, but our motivation is actually in our lab, we have built a lot of custom code, and we also had the need to use particle tracking in IWFM codes. And so that's why we built a tool that can actually serve this purpose. And we called it ICHNOS, from the Greek word, which means footprint or trace. And you can actually find the documentation in those links, and the code you can obtain from my GitHub repositories, which are all available in the presentations that John is going to share after that. So in order to accommodate different modeling approaches that we have developed in UC Davis, we designed ICHNOS to be mesh agnostic. Essentially, ICHNOS can actually trace particles in a in a standard numerical code such as mod flow and using finite difference or finite elements, but because we built some custom codes that are based on adaptive measure refinement codes, like the one that you see on the bottom of this of the screen. So we decided to actually take an approach where we can accommodate different methods there. In order to implement this to make it efficient, we developed this in C++, and it's actually a console application like ModFlow or IWFM. It's a console application. The majority of the code relies on efficient libraries like the Boost or the CGAL, which stands for Computational Geometric Algorithms Library. And for handling efficiently the input and output data, we use HDF5. We know for sure that our Ichnos code is compatible with Windows and Linux, and I don't see any reason why this is not compatible with Mac, although I have never tested. Last, as a feature, we designed it actually we support 3 forms of parallelizations, and I'm going to talk later about that. So particle tracking, the design of particle tracking is based on three main C++ classes. One class is the particle tracking class that is responsible actually to advance the particle in the flow field, and the particle tracking class has no actually information, is not aware and it doesn't know any information about the velocity field, about the groundwater model. All this actually, there is it only communicates with another the velocity class that holds all the velocity information. And again, in order to make this mesh agnostic, we split the velocity information into 2 classes. We use the position class, which holds all the structure of the data, and the velocity class that use only the velocity information. And we choose this actually, let's say, this design in order to make things independent so that we can work with different structures with the same velocity data. And then during particle tracking, all of those actually classes talk to each other in order to advance to do the simulation. So for the positional classes, right now we have implemented two cases where they cover actually all of the needs that we have encountered so far. One class is let's say it's a cloud positional class where essentially the velocity points are treated as a cloud of points in space, and then we use inverse distance weighting interpolation to calculate the velocities at the domain, or we use the mesh 2D class, and mesh 2D refers to the cases where there is a 2-dimensional mesh which is extruded in the vertical direction so that it forms a full 3D domain. And this is what is using in ModFlow or in IWFM. With the mesh, with this positional class, we can define the velocities at the element level. Essentially, you have each element has the velocity is constant, or you can define a velocity at the node level, and in that case, our code does a trilinear interpolation. Or the last case is actually you can define the velocities at the flows, at the faces. And so here we use what is called Thomas Ravier shape functions in order to do the interpolation. And this is very similar to what ModFlow ModPath is doing. Particle tracking is essentially an initial value problem, ordinary differential problem, right? And so we need an integration method in order to step in to advance the particles in the flow field. And we provide actually a number of very common integration methods. And it's worth mentioning that there are the last 2 methods actually provide an error estimation during the particle tracking so that they can adaptively reduce or increase the step if there is for example, if they encounter a flow field that has high curvature, then they can reduce the step to trace the particles accurately in this curvature. While the other ones, actually, you just use a fixed step in the beginning of the simulation and you are stuck with that. Now I'm going to talk a little bit about the parallelization. Essentially, we provide three forms of parallelizations. The first 2 forms they are actually, the goal is to trace particles concurrently. The multi-threading and the multi-core, let's say, parallelizations, essentially the only difference is that if you use multi-threading, you can exploit the threads that are available on our personal computer. But if you are using the multi-core, you split your workload into different processors. And of course, on a personal computer, you are actually have a limited processors, but you can use this method to run particle tracking in a cluster, where essentially you can then scale your simulation up to as many actually processors you have available, and there is actually linear speed up with the number of processors. The last type of parallelization is which is actually it's part of multi-core, but in this case the domain is split into subdomains, and each processor knows the velocity field only in one only in its subdomain. So essentially, let's say each subdomain knows the velocity information for a part of the domain and trace the particles only in that subdomain. And then when the particle actually has to move to the adjacent subdomain, then sends the particle to the next subdomain and continues the particle tracking. And this is actually was developed in order to accommodate some needs that when you actually have a very large simulation model that doesn't fit into the memory of your computer, then you use a cluster, and so you use you end up with a velocity field that actually is spun on across a large number of actually processes. But here I'm going to actually talk about this in the next examples. So first of all, we did a verification example where we use a very simple actually mod flow model, and where we define a constant head left and right to define a flow direction from the right to the left, and then we trace particles from the well here highlighted in blue, and trace them back with ModPath, which is a semi-analytical solution for the particle tracking, and with IGNOS using the ModFlow solution, right? And as you can see, both models are actually our model, the IGNOS model, actually has a delineated streamlines that are almost identical to the ModPath. For this example, we use the mesh 2D, but with phase interpolation, which is the closest type to ModPath. Now, as we said that we have developed this with cloud positionals, we use inverse distance weighting interpolation. And although inverse distance weighting interpolation is common in GIS in order to interpolate groundwater levels or surface elevation, it's not common actually to in this context of particle tracking, and that's why we needed to test that. So here we compare the previous example. We compare the ModPath case with a simulation tool that actually simulates the groundwater flow field using adaptive measure refinement, and then we use cloud and inverse distance weighting interpolation for the velocity. Overall, the two approaches match very well. There are some differences there, and these are differences actually due to the different the numerical time step in the particle tracking, and also to the difference in the grid between the two models. And then one last application, which is unrelated to IWFM, and then I'm going to move to IWFM application, is this one here, where we use hydrogeosphere. Actually, this is not my work. This is something. This is at some point a group of people they contact me to and ask me if we could actually use IGNOS with hydrogeosphere. And although I have never actually, when we wrote the code, we had never had in mind that hydrogeosphere could be used with that, but it turns out that it was actually very easy to connect hydrogeosphere with IGNOS. And in this actually is the work. What we did is they study the effect of the effect of cost curvature on submarine discharge. And to me, it was actually a very pleasant surprise to find out that we can actually work with a model that we never actually intended to work with. Now, let's move now to IWFM. And if you want to actually to do particle tracking with IWFM, of course, you have to use the velocity information. And the first question is actually, what velocity should we use? What information what interpolation method we can use? And the good thing actually is with IWFM, with the amount of output that IWFM gives us, we can use any type we want. For example, we can use element velocities, element interpolation, because the velocity, IWFM prints out the velocities at the cell centroid through this file, the velout file. We can use node interpolation because because it gives us, IWFM gives us the velocities as a tech-plot format. And last, we can use even phase interpolation, but here actually we have to do a little bit more work because we have to combine the information from different files and needs a little bit more work actually to do that. So before doing a particle tracking with Ichnos, we need actually to modify a little bit the input files of IWFM. Here I'm showing actually the SVSIM tool, which is the Sacramento that Yara actually described in the previous slide. And essentially what you have to do here is one need to go to the groundwater component main file and allow actually printing the velocity out file if they want, if one wants element velocities, or they should actually specify or uncomment maybe the velocity tech-plot file if they want actually node interpolation. And another very useful step is actually to tweak this multiplier, which increase the printing accuracy of the velocity field in the output files. And then, of course, you have to rerun and wait a couple of hours to finish this. And then once you have actually the velocity information from IWFM, you need to set up the Ichnos input files. The input files are pretty easy, I would say, to develop. You require one main file which has the format of INI, which is like a section with parameters. There is also a velocity input file with a section and parameters, and then there are some other actually file formats that one has to develop, like to define where is the bottom of the aquifer, and you know, how to structure, how to actually to pass the actual velocity field. And in our actually wiki side of the repository, you can actually find information for all of the file formats one you actually can need. And so one thing that is actually very useful for us is that we have developed a groundwater tools repository under this UCD groundwater GitHub. And here we provide actually quite a few functions of Python and MATLAB where one actually can extract the information from IWFM and then prepare the input files for Ichnos. And actually, in the example that I'm going to show you in the next slides, in order to extract the data from IWFM and set up the files, it didn't actually require more than 100 lines of code to do that. Now, SVSIM, although Yara had already described a little bit about that, I'm going to actually say a few things. First of all, is a transient groundwater simulation that spans for 42 years, like 504 months. Now, the groundwater travel times in the model, they range from several decades to multiple centuries. And a frequent actually request in the lab was the ability to capture fully the trajectories of the particles. And this was not possible if we actually do the particle tracking only within these 42 years of the simulation. So we included an option actually to repeat the flow field or a portion of the flow field, if you want, after the 42-year period. So here in this for this presentation, I created a demonstration here where I did a particle tracking run by releasing particles from 300 meters below the water table, scattered across the entire area, and trace them backwards. And we used two types of velocities. First of all, we took the last 10 years of the simulation and we averaged the velocities. And then we used the last 10 years of the transient field and we repeat it over and over until all the particles actually have completed their trajectories. Here in this example, I use element-based interpolation for the velocity estimation. So here are actually some of the results. First of all, in this plot in the left side, you can see the starting location. You can see these are about 5,000 particles scattered uniformly, but we avoided actually place them on the boundaries. And then this graph shows the end locations using the steady state velocity field and the transient state velocity field. And here in this in the right upper corner, I'm showing the travel time that of the particles, the histograms of the particle of the travel time. And you can see actually both steady state and transient state distributions are very similar. And here also I have plotted, I have put with dash line the limit, the 42-year limit which indicates actually how much, which is actually the time span of the simulation, of the SVC simulation. And then what I did is actually I grouped the well in this first figure here based on the travel time to actually to complete their particle simulation. And so all the particles that are actually red here, the simulation was finished before before actually the 42 years. That means that all those red areas could have been simulated with the standard SVC model, right? But all the blue areas require actually a lot more time for than the horizon of SVC. And now I'm going to actually conclude my presentation by showing a few streamlines. So here is actually one example that shows what the trajectories will look like if you use element-based interpolation. And so the red one, which is actually the transient state, shows that during the month, because the flow field is transient, the direction changes in some elements. While the blue lines is actually just a straight line because there is no change in every month. Actually, there is I cannot really draw any conclusion that, pretty much the transient and the steady state match very well, or they don't match very well. I would say it depends on the area. In some cases, it matches very well. Here, it just happened actually I'm plotting some streamlines that they match, but in other cases, it's quite different. Here is one example where they both start from far away and they end up on the river in both cases. One more example that I would like to show here, and this is, and actually I choose this example because this is a situation that one can encounter in using element interpolation. You can see here that the flow direction for this element is actually point to the southwest, to the southeast, and this actually points to the north. This means that the particles actually, the particles when they approach at the end of this of the interface between the two elements, actually they start actually going up and down in the layers until actually they exit here. And in that actually particular case, probably this element points down. So they say the trajectory looks actually quite weird there. And last, I'm going to talk about computational efficiency. This generalized and mesh agnostic design, of course, introduced an additional computational cost. So compared to Modpath, IGNOS is going to be much lower. And primary reason for that is that we don't do analytical. We don't calculate analytically the exit point at the elements, but we just do always numerical integration. And also, we don't use what is known as time-of-flight methods, where you take an element, you convert this element to a unit space, you do your tracing there, and then you convert your results back to the actual 3D space. We just always do interpolations on the 3D space, and this is a little bit more time-consuming. And the reason that we are doing this is because there is no guarantee that there will be an element that is to rely on that. So in the cloud interpolation, there is no actually element to convert on a unit space. However, we provide the parallel capabilities, which mitigate some of this overhead, and actually it scales up linearly with a number of processors. And the last thing that regarding computational efficiencies is that the transient simulations, especially with C2VSIM and CVSIM, because they are monthly and because the velocity, the groundwater flow is generally slow, is going to be overall the simulation is going to be slow because you have to take very small steps to respect those monthly steps. You cannot take a step. Actually, you cannot take a large step that is going to require, a year let's say a year, because then you're actually skipping steps like that. So you have to take very, very small steps in order to actually to capture a transient state simulation. And yes, some next steps about this project is we already actually started. We have already worked with to implement random walk particle tracking. Currently, this is available only for cloud type positional configuration. It's not available for the mesh 2D, for the mesh, let's say, structure. And also it is an experimental functionality. We haven't actually fully debugged that yet. And also we use a stochastic particle tracking. And this is actually something that we have used at our lab quite a few times. And I'm showing here 2 links that point to AGU posters. And here in what we actually we treat the transient flow field of the C2VSIM and SVSIM or IWFM models as a pool of velocity states from the probabilistic direction sampling. I hope that I will find time to finish up the publication about that. Last one is we've developed a Python API that is going to enable to work and run IGNOS directly from the IDE, so you can have actually a better streamlined workflow, and you don't have actually to switch between console and preparing file. You can actually do everything through Python. And I think that's about that. And I'll be happy to take questions.
Thank you, Georgos. Are there any questions? Mohammed?
Okay, Mohammed.
Yes, hey, Georgos. So does the code really have full functionality of steady state and transient state condition?
Yes. Yes,
Okay.
it can interpolate either linearly or using or constant for each step. But of course, you need a transient state flow model, right?
Right, you can, for IWFM, for example, or C2VSIM, you can throw particles around the well, like one set of the particles around the wells, then you can track them backward given transient flow field, right? So there is no need to average first to get the path, and then, okay.
No. But at the scale of the elements of C2VSIM, even the fine grid, which are about a mile length, and then you will not really see those nice, capture zones that you get if you use a highly detailed model.
Right. Okay. So another, that's the first time I know it's a transient. All of I know about this one is the steady state. That's very good. And then have you compare the result of the code in terms of the transient flow field with any other available codes for the finite element, like in FeeFlow, they have a 2 particle tracking code. Have you compared your code with the result?
Not with FeeFlow, because I don't have access to the FeeFlow.
Oh.
Yeah.
Okay. Well, that's very good. Thank you, Georgos.
Thanks.
Rita?
Hey, Georgos, great work.
Hey,
thanks for the presentation. Hey, one question regarding the parallelization. So you talked about the multiprocessing. Is it are you using MPI or are you using multi-threading like OpenMP?
I use MPI, but it doesn't really matter. I think in terms of when you code on C++, I think there is a that doesn't matter actually what library is building is based on that. You can use MPI or OpenMPI and it can run, I think.
Okay, yeah, I noticed that you have used sort of domain decomposition type, so that's why you get MPI utilized. Yeah, that's good to know. So you said that you get a almost linear speed up.
For when
yeah.
for the multi-process for the multi-core simulation, yes. For the multi-threaded, not so, because there is a I'm not quite sure. I mean, what happens with the multi-threaded simulation, but for the multi-core, yes.
Right. Yeah. Because I was trying the multi-threaded and then I couldn't get the parallelization. Like I could get like 5 times. I mean, it's some at some point you lose the speed up. It's like after you use like 8 or 9 threads in a single. I tested just a single CPU. So after like certain number of threads, it's the parallelization, kind of loses its the speed. I mean, well, I guess I haven't tested in maybe a cluster or so. It's good to know. I'll probably be in touch with you.
Sure. Yes.
Yeah.
Well, with multi-threading, there is some locking behind. There is some locking mechanism that actually can slow down your overall simulation where you don't have that. Of course, there is the downside of multi-process is that you have to every process needs to load the entire velocity field and the entire data. So with multi-threaded, you just read the data only once in your computer. But I think nowadays personal computers can accommodate can easily load. If you have let's say 12 processors, you can easily load 12 times the, let's say, the IWFM flow field. That's not a problem.
That's good. Thank you.
I have a question. So you said that with IWFM you can use 3 separate outputs. When you want to do particle tracking, did you compare them all? Like, do they all give similar results, or one is more preferable than the other? Are there any comparisons like that?
Yes, I have. In most cases, I use element because it's the simpler, actually the simplest velocity type that I can get, and in order to avoid this zigzag between the elements, I treat those velocities as cloud of points located at the centroid. So with the inverse distance weighting interpolation, there is some smoothness there. But it's not really what the velocities are meant for each element. So there is some kind. I mean, let's say you polish the corner of your simulation somehow artificially that way. I have done in the past with Node, and I think maybe this is actually the best case. I think it's best to do with a node using the tech plot velocities. I think that's the best case. So you are more close to what IWFM actually has calculated, and you get some count. You get away with those actually artifacts between the elements. But I think that I remember that I had done actually some comparison and they look pretty similar. Yeah.
Okay.
But I don't really. Yeah, probably that's a good thing to do again. With phase interpolation, it requires actually quite a lot of a lot of output. I had done some once, but I was never actually completed this work. So yeah.
Thank you. Any other questions? All right. Well, great. Well, thank you, everybody. Thank you for your time to our presenters. I will go ahead and post the recording. Unfortunately, I forgot to turn it on for my own presentation. So again, thank you so much. Have a good weekend. And I guess we'll see you guys next year in our next users group meeting. Hopefully we'll have interesting topics like this again. Take care. Thank you.
Thank you.
Thank you.